In this video, I'll be showing you how to program matrix rain on this calculator. Something I enjoy doing is going to second-hand shops and finding interesting electronic devices that are up for sale. In Australia, we have a couple of big stores. They're called opportunity shops, or op shops for short. And sometimes you find these interesting electronic devices like crossword solver and one of those personal diary spell checkers. But occasionally I actually find something a bit more interesting, these calculators. This is a TI-83 and it's a few years old now, and you can get these for a few dollars, maybe 10. I actually got this one for $2. Can you believe it? Another calculator similar to this model is the TI-84. And I guess when I went to high school, our calculators weren't as fancy as this. Having something that can, like, graph sine waves, I think is pretty cool. So I've actually collected a bunch of these calculators. Here's another one and another one. And this calculator here is probably the latest one. It's CAS-CX. These are about $250. But the calculator that I'll be programming is the cheaper model, something you can buy for about $10, the TI-84. But did you know these calculators actually have the Z80 microprocessor as its CPU? And since I'm a bit of a Z80 fan, I just have to program something on this calculator. So this video will go through step by step how to program these two calculators, the TI-84 and 83, using Z80 Assembly. But I thought, what better program to do? Something similar to the opening credits of the Matrix series, where characters fall down from the screen at different rates and characters change at different speeds as well. And this is what I'll be programming, characters that are falling down the screen and at different rates and changing also at different speeds. And you can program this too, just follow along. There's a wealth of information online regarding the TI calculator and all its features. And there's a really active community out there. Some of the popular websites are the ticalc.org, wikitibrandonw.net, and probably the biggest resource site is the Semitech. I think it's pronounced Semitech or Chemtech, semitech.net. It's got a great active forum, and if you click on resources, you just pick your calculator that you have, the TI-84, and it's got information on how to use it and how to program it. It's even got a wiki that contains a heap of material about the details of the TI calculator. Another resource I'll be using is the Texas Instruments TI-83 Plus Development Guide and the TI-83 Plus System Routines. So how do you start programming the calculator? There's a link, how to get started programming Z80 Assembly. Click on that link, and in summary you need an assembler, a text editor, a calculator, or an emulator. One of the most popular assemblers is Spasm. You can download this and install this on GitHub. It's got heaps of information about how to build it and install it. The main advantage of using this compiler is that you can't just compile a binary and load it to your calculator. You need to sign the file to convert it to a special 8xp file. And the calculator will only understand an 8xp file. And that term is called signing the app to make it work for the calculator. SPASM will do this for you. But I'm not going to program using these tools. I'm going to go directly online and use these tools, JST5, which is the online emulator, and SourceCoder 3. In order for SourceCoder to work, you need an existing calculator and you need to extract its ROM. To do that, there's a tool called ROM8X, which can be used to extract the ROM from your calculator. Once you've got the ROM, everything will work just fine. And before we get started, here's a message from my sponsor. Have you been dreaming of that electronic project and want to make it a reality? Just like my ultimate expansion board for the Tech 1F. Well, head over to PCBWay to make your dreams come true. PCBWay are the leading printed circuit board manufacturer. They make high-quality multi-layer boards with a 24-hour production time. Just enter the board dimensions and upload your Gerber file, and that's it. Once posted, a neat box will arrive with your well-packed goodies. Just look at the quality of this board. They also do PC board assembly, CNC machining, and 3D printing. You can even order user project boards directly from their website. For $5 off your first order, click on the link below, PCB Way, Prototype, the easy way. So when looking at source coder for the first time, it'll ask you to create a new file or open a project. I don't have any projects yet, so let's create a new file. It'll ask you which calculator, the TI calculator, and we're doing a Z80 assembly program, so click on Z80 Assembly. And to the right hand side is the calculator. I can click on the sidebar and pops open the calculator. I've already loaded the ROM to this calculator, so it's ready to go. So every program must start with this TI plus include file. What is the TI plus include? It's a file that references pretty much all of the methods and constants and variables related to the calculator, so you can easily use words to write your code. So y min t is OC. We don't need to know OC, we just need to know y min t. It's extremely well documented. It has an important method called bcall, where we can easily pass in the firmware function to call the desired function. And here are a list of firmware calls. There are literally hundreds of them. They're all well documented. It also has constants for setting particular flags and the bits on those flags. So we start off by always starting at user mem and having BB and 60 at the start. This just tells the calculator that it's an assembly program and can only be run via the assembly call. So let's start coding. Let's now set up some labels. I like to have a start, and like with any graphical engine, you have an initialize and a draw loop. And we'll also like to exit cleanly with a key press. So let's say if we press enter, we would like the program to exit. First, we've got to check for a key press. So I'm going to call CSC. This polls the keyboard and compare it to SK clear. Again, these constants are all defined in the TI plus include file. If it's a clear key, then we jump on 0 to initialize, start again. If it's the enter key, we check if it's not the enter key. We'll just go back to the draw loop. And if it is the enter key, well, we just call return, and that should exit from the application. I did have problems exiting this application, so it was recommended to call this function, jforce command no char. Slightly controversial. You've got to read my notes about this. It will work, provided that the program is run via the basic calculator shell and not any other program running on the TI. And we'll just label this as key poll. But let's now get a character onto the screen. How do we do that? Well, first we've got to understand how the LCD screen actually works. So what's the format of the LCD screen on the TI calculator? Well, it's 96 pixels across and 64 pixels down. The calculator has a special bit of memory to store this column and row data. It's called pen column and pen row. So if I want to place the letter A, let's say, in the middle of the screen, starting at the top right-hand corner of the character, this is what I'll do. I'll update pen row with 32, which is the middle of the screen in rows, and I'll save that to the pen row address. I'll load A with 48, be the center of the columns. I'll save that to pen column. And then I'll load the letter A to register A, and I'll call a special firmware method called vputMap. That looks at the pen row, pen column, and writes the letter A in that position. vputMap, it would give me the flexibility to put any character at any position. And running this code will give me the letter A right in the middle. So I'd like to put a character on the top left-hand corner of the screen. Let's load B with the row, 0, and let's load C with the column, 0. And prior to that, let's clear the screen by calling clear LCD full and home up. Let's now save the row. So load A with B and load that to the pen row, and load A, C, and load that to the pen column. Now let's print the letter A. So load A, register A to character A, and call vputMap. Let's compile this. So to compile it, you can click on check. It will compile it. Oh, it says a name is needed. So we need to give it a program name. Let's call it matrain. Now this is really important. It needs to be capitals. otherwise it won't transfer across. So capital program name, hit check, that assembled perfectly. Now I'm going to show you this once, how to transfer it to the emulator here and to run it. So we're going to do test, that will transfer it across, successfully transferred. We go to the calculator, and to run this program, this is important, we hit second and catalog, and now we need to use the arrow keys to go to ASM, hit enter, and then we hit program. There's our matrix rain program. You can hit 1 or enter, matrix rain, and press enter to run it. And there's our letter A. Perfect. And you can see on the right hand side of the screen, you have like a little weight indicator there. So hopefully if I press enter now, it should exit the program. Enter, done, perfect. From now on, since I've got the ASM program on the calculator, all I've got to do is hit enter again. So hit enter and it should run the program without me having to type ASM and program matrix rain again, and hit enter to exit. Okay, let's get this letter A moving down the screen. All right, we need to update the B register. That's the row. We're going to load D with the rate of change downwards. So we'll load that with 1 pixel down. Currently A is the row. So we're going to add A to D. Now, we've got to worry about if it goes off the screen. Remember there's 64 rows down. So if I AND A with 3F, once I get to 64, it will wrap around to 0 again. And then we load that back to B, which is our row. All right, hit test, transfer across. Let's hit run. And we've got the A moving extremely fast. Let's see if we can slow it down so we can actually see it and get rid of this waiting for key bar on the right hand side. So let's put a delay in there. This is a typical 16-bit delay. Load HL with, say, 300 hex. Load DE with 1. And then delay. We do a subtract with carry DE from HL. And then jump relative, non-zero, back to delay. And also let's get rid of the run indicator. So we call the method run indicator off. Okay, let's give that a test. And there you go, the A is moving down the screen as you can see now, a bit slower, and that run indicator is not on anymore. Plus the letter A wraps around the screen perfectly. Okay, next thing we need to do is to randomly change the character from A to something else. Let's load E with the rate of change. Let's call it 17 hex. Some number between 1 and 32 hex. And this time I'm going to load A with R. Now R is not a random number, but a number that increases on every clock cycle. And we're going to compare it with E, and we don't want to change that often. So if E is less than R, so no carry, we're going to skip the rate change. So we put skip rate as a label. But if R is less than 17 in this case, we need to get a random character. So I'm going to call a method called randchar. So now we need to generate a random number between 0 and 25. We're looking at letters of the alphabet here. But to start with, we do need a random number generator. And here's one here. Again, you can pause the video and type this out. This is just straight out of a TI random number generator document. It plays with some variables and adds them together, and it uses a seed 1. Now seed 1 is actually a memory location on the TI. To initialize that, we can go right up to the top of the program and call rand int. So this generates a random number between 0 and FF. Let's generate our random character, randchar. So we're going to call random. A now is between 0 and FF. We only want 26 characters, so to make it easier, just go to 1FH. We make the number between 0 and 31. I compare it to 26. That's our letters of the alphabet. And if it's greater than 26, no carry, we just call randchar again. Now we're going to offset that value A with the ASCII character A, capital A, which is actually 41 hex, and then return. Now, because this is all hard-coded, I'm going to just put in a bit of a cheat code here to load this register A back to the hard-coded value up here. So I'm just going to put a label here, temp lab. And then down here, I'm going to load temp lab +1, which is the letter A, not the load A. 3E is load A, and then the next byte is A. I'm going to load it with A. Now I'll have to remove this later, so I'll put a note down here, remove later. Okay, let's give that a go. Okay, hit enter and there you go. We've got the character falling down the screen, changing at random rates with different characters and at different rates too. But this is a bit limiting and it's called hard-coded. We really need a better way to produce our streams dynamically in the code, where we can create multiple streams at different lengths and at different speeds and change rates. And this is the way I've decided to construct the stream data. There could be a few different ways you can do this, but this is the way I've gone down. First, we have streams. So what does multiple streams have? One or more stream. And then to end the streams off, have an end of stream ID. What's in a stream? It contains three things: a stream header, character data set, and the character data set can be between 4 and 7 sets. That's just something I've chosen to fit into the screen well. And an end of character ID, just to know when the stream is over and we can look at the next stream. A stream header, what's in there? Only two components: the column of the stream and the speed of the stream as it moves down the screen. How fast will it move down the screen? The character data set has 3 bits of data: the row that the character is in, the ASCII character that will be printed to the screen, and the change rate of that ASCII character. And lastly, the inner character ID and inner stream ID, just use FF there. So this is the data in streams. Now it looks pretty confusing, but let's go through this using that stream pattern I've just defined earlier. This is an example of 2 streams. The first 2 characters contain the stream header, so we're looking at column 1 and a speed of 3 going down the screen. And then we've got the character data set. The first character starts at row 00, it's a character A, and 14 hex is the speed that it will change at. Then we've got the next 3 character set. We've got C, and then we've got D. And then we end the stream with an FF. And then we move to the next stream. We start at column 9 now, and we've got E, F, and G. And end of stream, and then end of streams. And when all done, we should get 2 columns. First column has A, B, C, D. Next column has E, F, G. And hopefully they'll move downwards. So let's now implement this structure into the code. In the initialize block, I've decided to have 12 columns, and I'll load the columns to the register B, so 12. And we're going to start at column number 1 in terms of where it's placed on the screen in pixel size. We need to save the stream somewhere in RAM. Now I could add it to the end of this code, but the TI has safe locations to store RAM. One of those locations is called Save S Screen. Now this area is only used when the calculator automatically powers down. After a timeout, it saves the screen, so it's free to use provided that automatic power down is disabled. And to do that, we can set a flag, and I'll do that in the start area. How flags are set on the TI is quite clever. It uses the IY register and then the index of the flag, which is APD flags here. And one of the bits is called APD running. You can either set it or reset it. In this case, we're going to reset it. All these constants are defined in the TI plus include file. Okay, so let's create a label called next stream, and that will iterate through the 12 streams. So now we're going to save the first bit of data, which is the column, to the save screen. So we have a column, and then we need to create the speed that it scrolls downwards, increase HL to the next location. We need just a random number, so we'll call random. We only want to look at speeds between 1 and 4, something I've decided, so we'll just mask out the top bits and just leave 0, 1, and 2, and 3. Increase it so we don't get a 0 speed, and save it back to memory, and that's it. Now we need to generate the character set. I've decided in terms of the screen height and how many characters you can fit, between 4 and 7 characters is great. Let's get another random number, so call random. Mask it to 3, so we just get 0, 1, 2, and 3. Now I want to add 4 to it, so we'll add 4, which gives us a number between 4 and 7. Now we need to save this count. We'll save it in E because we need to know how many times to loop around to add the next character. And now we're going to start with the initial row. I'm going to save that into the D register. So the initial row is 0. Okay, so now we're going to iterate another loop to generate the next characters, E times. So we'll just move to the next memory location. The first value we need to save is the row, so we just load the contents of D to HL. First row is 0. Now while we're looking at the row, we'll just increase it to the next row down, which is 8 pixels down. So load A with 8 and add A to D, and then we save D again, so load DA. Okay, now we need the character, so we increase the next HL. We've already created a function to generate a character, rand char, that will return in the register A the new character. But if I go down to rand char, remember we had this bit of temp code here. We don't need to do this call anymore to update the char. We'll actually just return it, use the return value here. So we can get rid of that there. And then we just load the value of A to HL. The next information we need is the speed or the rate of change that the character will change at. I've decided a number between 1 and 32 will suit. So go to the next memory location and another random call. So I can just cut and paste this. But in this case here, we want to just mask out 1F. So we get a value between 0 and 31. And we increase it to get it between 1 and 32 and save it. We've stored the number of characters in the register E, so we decrease E, and if it's 0 we exit, but if it's not 0, so jump relative, non-zero, back to next char. Alright, that will save up to 7 character sets. So we're at the end of our first stream now. We need to increase HL again, and we need to save the end of stream character. So load HL to Ada HL. We're going to move to the next stream now. We can increase HL, and remember our column now is on 1. We just want to add 8 to it so we can move to the next column. So load A8, add A to C because we did save the initial column in C right up here. And then we load it back to C. Alright, and now the register B has got the number of columns. It's at 12 at the moment, so we're going to DJNZ. That will decrease B, and if it's not 0, it will jump back to next stream. Oops. And when that is 0, we've done all our 12 streams. We just need to finish off the last stream with an FF. So just cut and paste this, and HL is already increased at this point, so we don't need to do the increase, and that should be it. That should be our data saved, our 12 data streams. Okay, now we need to iterate through these data streams and print them to the screen in our draw loop. Most of this draw loop is actually set up already. We just need to modify a few things. Instead of the hard coding values, we'll then load them up from the RAM location. And then we're going to look at those end of stream flags, the FF, to decide, are we going to move to the next stream or not. So we can remove B and C now. They were just hard coded for the columns and rows. That will be grabbed from the actual data in RAM. So in our draw loop, point HL to the RAM location, remember what it was called. save S screen. And with these iteration loops, sometimes it's easier to start with one byte off from the loop. So the first instruction can be an increase of HL to look at the first bit of data. So we'll do that. Okay, so we just need some labels here. New stream. Okay, increase HL. So this is the column data. We're going to load A with the contents of HL to get the column data. Now remember, if it's FF, it means it's the end of stream, so compare with 0FF. If that is 0, it means they're the same. We just want to go to the key polling routine and repeat the loop again, the draw loop. So check for key press, everything's printed, check for key press, otherwise reprint the screen again. So we've got the column. In A, we'll actually save it to C. So when we print the character out, it knows which column it is, the current column we're looking at. Now we're going to look at the, just tidy this up. Now we're going to increase and we'll go to the next HL, which is the speed of the stream. And we're just going to store that in D for now. So grab it, location of HL, put into D, and then increase HL, and we'll get our first character. So we need some loop to loop through those character sets. Call it print char. We're going to get the row because the first value is the row, so store that in A. Is it FF? So is it the end of stream? If it is, well, it's the new stream. So we've finished with our current stream. Now we just jump back to the next stream. But if it's not 0, it must be a character. First value in A was the row, so now we can go back to original code and say load pen row with A. The row now needs to change to the next row downwards based on the speed of the change, which is saved in D. So we can remove this 1 hard-coded because now we've got D is in the row, is the speed of the stream. And instead of loading into B, we'll actually save it back to the current memory location. So when it prints next time, the row will be 1 step down. And we've already got C as the column, so we just keep that as is, pen column, save it into A, and now we need to get the character. So we increase HL, load A with HL, which is the character value, so that will be the ASCII character A to Z. We can remove this temp label, that was for the hard coding example version. We don't need A anymore, this A, because it's actually loaded into A from the memory, and we just call vputMap. But vputMap actually destroys some of the registers on the CPU. In the reference manual of vputMap, you can see it destroys all registers but B, C, and HL. Need to protect the DE register, so what we'll do, we'll push DE before the call. That will save it onto the stack, and we'll pop DE after the call's done. Now we've got the rate of the character change, so we'll increase HL, and instead of loading E with a hard-coded value, we can actually load it with the value generated on the stream, so HL, and we'll continue with the same. We're getting A with register R. We'll compare it with E, and if change rate is less than the register R, then we'll skip the rate change, otherwise call the random character and generate a new random character. But in this case here, we actually got to save it back to the character data set. Now that was 1 step behind where HL currently is, so we'll decrease HL, we'll load HL with the new random character and increase HL to go back to where we are, which is the change rate. And then we skip the change rate, we just fall through down to here. What we'll do, we'll go to the next HL value. So this will be the next character data set, or if it's FF, it's the next stream, but that is already handled up in this print char. So if it's end of stream, we go to the new stream. So all we need to do now is jump relative to print char. We have this delay here, that was to slow the character down on the screen, but since we're printing a lot more characters, it should be a lot slower, so we can remove this delay, and that should be it. And this is the bulk of the code here. We've got streams that are saved in memory, and then iterating through that memory, printing the streams to the screen. I'll do a check here to make sure it compiles. Yep, so that all compiled properly. And turn the calculator back on, transfer it across, and hopefully we'll get multiple streams coming out when I press enter. Let's go. Oh, and there you do. You do have multiple streams, but it's not looking good. We've got some streams. Some of these bigger ones are just the characters are overlapping each other. It's not refreshing the screen properly. We've got the smaller streams, or some of them seem to be working, but some aren't, based on basically their stream speed. We need to fix this up, and this is effectively a problem with the printing routine. vput map, just a bit slow. We need to make it a lot faster. If we look at vput map, there's a flag that you can set called text write that writes to the graph buffer instead of the display. So when requiring fast screen updates, a better way to do this is to set this flag, and once you have the data stored in the graph buffer, write it directly to the LCD screen. And in the software guide, it talks about writing directly to the display buffer, how the LCD column and rows are set up. And with typical LCDs, you can send instructions and data. So an instruction of 80H and 20H will move the cursor to the top left-hand corner of the screen, and then a data command will send the data to the screen at that location. The Brandon Wiki actually has the fast copy, and it provides a few routines here that you can use. And the routine that I'm going to use is this one here. How it works, it looks at the graph buffer, and for 64 rows and 12 columns, it grabs the data from the graph buffer. At the same time, it clears the data for the next screen refresh, and then it outputs to port 11, which is the data line for the LCD. Okay, so let's set up some constants now for the output ports. So we've got the instruction port at 10 and the data port at 11. Let's now set the text write flag. So vput map will only write to the graphic buffer instead of the screen directly. Now, where is the graph buffer? In the development guide, when you set the text write flag to 1, it will write to the graphics buffer, which is called plot s screen. So at this point, when I do bcall vput map, it actually won't update the screen, it will just update plot s screen. So when we finish the updating of the streams, we need to now print the streams. And I'm just going to call a label here called print LCD. And this is just a cut and paste of the code that I've just saw on the wiki site, but I've updated the labels to be meaningful and easy to read. And there's plot s screen. Also, when the streams are finally updated, I jump to key poll. We need to change that now. We need to change it to print LCD. So if I go a bit further up here, new stream, if all the streams are over, we now go to the print routine. Okay, that should be it. Just a few lines of change to hopefully get the screen to update it a lot quicker. Let's compile that. No warnings, great. Transfer it to the calculator and hit enter. Wow, look at that, much better. And it's quite fast actually. So there's no streaking or delays. I guess with all this movement, there's a bit of flickering. LCDs are notoriously known for ghosting and poor refresh rates. There's our matrix rain done. And if I hit the clear button, it should reset the streams. Yep, there it goes. And clear again, clear again. And you can see the randomness of the stream lengths and obviously of the characters as well. But hey, if you're still watching this video, you're probably saying to yourself, well, they're just ASCII characters. What about the actual font used on the Matrix intro screen? So my understanding, that font is called Katakana. So let's go one step further and get the Katakana font loaded. One way to install a custom font is to use the font hook. And again, on the Brandon Wiki is the explanation of how this font hook works. It's got a fairly good example here of how the font hooks work, setting it up, and also how to set up the custom character font. So here is what you need to do to implement the font hook. We only need to do this once, so in the start routine, we do a load HL to my custom font hook routine. And we also need to load register A with the current memory bank that we're using now, in this case, it's just number 1, but the TI has multiple memory banks. Just to be sure, you can actually do an in command, save to letter A, and we can fetch from the port, memory bank port, what the current bank we're looking at. So memory bank port's a constant. What port is the memory bank port? It's 06. So we'll put that up there. And then we just need to do a B call to the routine set font hook. And that sets up the font hook. But once we set up the font hook, even if we exit the application, it will still override the default font routine. So at the very end of the code, before we exit, we should reset that font hook. So clear font hook, be call clear font hook. All right, let's go down to the very bottom. So how do we program my font hook? Create the label. And here's the code. First, you are required to put in 83 hex at the start. It doesn't do anything, but it tells the TI calculator that this is a hook. So when this routine is called, there are 2 parameters that are passed, A, the register A, and HL. So A is what type of font that we need. Now by default, I'm looking at the small font, so that should be 0. So we need to check that A equals 0. Otherwise, it's going to use the large font, and then we exit, and it uses the existing font routine. HL contains the font table offset of the current character. Now, so it's the ASCII value multiplied by 8. It's already indexed. So we make sure A is 0 because we're looking at the small font. Otherwise, if it's not 0, we exit. We're only looking at capital A to capital Z on our ASCII characters. So I'll multiply ASCII A with 8 to get 0208 hex. And I use this to index my own local font data, which is down here. And then I re-index it to get the actual font because they're 8 bytes long. And lastly, I store it back into this memory address called sfont record. That's what's used for the vputmap routine to find the font. And then I just remove the carry flag and exit. So what's this data format for the font data? Let's have a look now. So let's say I want to print a custom Katakana character like this one. How do I do that? Well, I'm going to use the small font to do this. It just gives me a bit more flexibility in the width. And this is the structure of the small font. The first byte is how many columns that I'm going to use. In this case, 6 columns, starting from the least significant bit. You still need to set all 8 bits. And the next 7 bytes contain the graphical structure of this character. And as you can see, if you can kind of squint at it, where the number 1 is, or a bit set, is where we're going to draw the pixel. And so this structure will actually convert to this graphic. So as you can see, you can create any type of custom font or characters that you like. Okay, let's get this font loaded. I don't like cutting and pasting, but all the code is in the GitHub account. So here is the font data that I've generated based on the Katakana font. I've got all 26 characters based on the 26 A to Z characters on the English alphabet, and I've separated into byte format so you can easily see where the bits are set, the characters are displayed, or the pixels are displayed. Alright, that should be it. We've got our font hook set up. It will retrieve the index data from this font table, store it back into sfont record, and hopefully display it to the screen. So for our final go, let's just check that it compiles. Perfect. Transfer it to the calculator, and cross your fingers, hit enter. Whoa, there we go. Katakana font. Looking just like the Matrix Rain screen now. Well, almost like the Matrix Rain screen. It's working perfectly. But there's one more step to do. This is on a software emulated calculator. Let's actually put this on the actual TI calculator itself. So to get this program now onto your calculator, all you do is hit the export button. It will automatically download the Matrix Rain file. There it is there. And it's already signed as an 8xp file. Texas Instruments provides a program that helps you connect your TI calculator to your computer. It works on any platform. It's called TI Connect. Now you just got to plug in your calculator using a USB plug. Once connected, the calculator will appear on the screen. There it is, TI-84. Click on this tab here, which will go to the workspace. You can see all the local variables on the calculator, but we click on this button here to upload from your computer. Find the file, there it is, Matrix Rain. Hit open. It's automatically recognized the file. It's called Matrix Rain. Put into RAM and hit send. There it is there. Let's now look at the calculator. Okay, I've loaded the program onto the calculator for our final test. All I need to do is call the assembly function, second catalog, scroll down to ASM, press enter, hit program, there's Matrix Rain, hit enter, and enter. And there you have it, Matrix Rain. And there you have it, it's a cool little program, something you can show off and impress your friends with. I hope you found this video interesting and that you know a bit more about the Z80 programming language. Also, if you can see some improvements for this code, please let me know in the comments below. I am a bit of a novice to the TI BIOS on these calculators, but I think I've created something pretty successful here. Thanks again for watching, and bye for now.